Alright, Chapter 5 is called Chemical Bonding, Part 1, and Chapter 5 is called Chemical Bonding, Part 2. So the next two chapters are all about bonding. And why is that so important? Right? It relates to many chemical properties of stuff. Okay, and so the author uses here the example of opioids, and more specifically, what you see here is the poppy seed, and of course, what we extract from the poppy seed is morphine. And morphine is effective as a pain reliever because it binds to the opioid receptor in our neuron system. Now, I understand that some of you have various backgrounds in biology, but you've probably all heard of the lock and key type system, and that's how everything works in the human body. Not everything, but bonding, binding and enzymes and adrenaline and all these things. And so morphine just happens to have the right shape, and shape is directly related to the way the atoms within a molecule bond. And so if we understand more how two atoms interact, and then 3 and then 4 and then maybe 400, we can understand the behavior of all the way to DNA, which has 300 million base pairs and millions of atoms in it. And so, but to make a long story short, and for the purpose of this chapter, we're going to focus on basically just two atoms binding for now, and then some more, and we're going to look at shape. We're going to take shape into consideration as well, right? So we can explain chemical properties if we know how things are bound together. We can understand why why hydrogen and oxygen bind in a 2-to-1 ratio and not in a 1-to-1 or 3-to-1 ratio. And it's all about electronics and interaction of these two atoms together. And interestingly enough, if you pump an electron into this system, or you take one out of this system, then those would be stable. But bonding theories are going to directly relate to the chemical formulas of our compounds. And take note that these are here covalent compounds, which we know already are two nonmetals binding together. And then of course the shape. Right, we can predict the shape. Now I've drawn this, and if you've paid attention, I don't draw water like this. Water is not linear. Water is bent, and there is a reason for that. And so these next two chapters are looking into starting with very simple bonding theories. One that's about 100 years old called the Lewis theory, and we still use it a lot in science, and it explains very simply how the shape and the atoms are connected with each other. And so this is chapter 5. It's mainly on Lewis theory, and then valence shell electron pair repulsion rule, which is Vesper theory short or abbreviated. It essentially says that if you have two atoms connected together, or let's say 3, and well, okay, I have an oxygen there, but it was supposed to be just a random element. But if you have a central atom here and a number of atoms attached, that these atoms will go as far away from each other as possible. They repel each other, right? You've got electrons repelling each other here, and so you get a 180-degree angle. And then things get more complicated as you have 3 regions of electron density, or 4. You can have now, and this is not an oxygen. It's just what I've chosen as a symbol for a central atom, right? If you have like a lone pair of electrons here, that takes up space too. So now all 3 regions repel each other, and then you have to consider 3-dimensional space, and things get a little bit more complicated to visualize in 3-dimensional space. But that's what Vesper theory is, and we're going to talk about that in detail here in chapter 5. And then chapter 6 looks into more advanced models. One is called valence bond theory, and then molecular orbital theory. And each of these has its own merits. It's more or less a step past the first one, and then molecular orbital theory can explain some things that the Lewis theory cannot, and that's all there's to it. So this is just a preview. For the third time, I'm going to bring up electronegativity. It is related to the bonding of nonmetals, right? It tells you whether a bond is polar or nonpolar or ionic. And so if you remember, electronegativity is the ability of an element to draw electron density towards it. I'm not going to explain it again. It's just it seems like I just recorded that lecture yesterday, and maybe you just watched it 2 days ago. So just remember, fluorine is the most electronegative, and then the trend is down, and towards it is an increase in electronegativity. And so if you have a large difference between two atoms, if you have a metal and a nonmetal, for example, you usually have a large difference in electronegativity, and you get an ionic bond where the electrons are completely transferred from the metal to the nonmetal. And if you have two nonmetals, you get different kinds of scenarios. You either have uh, uh, equal sharing, so it's nonpolar, or just a slight difference in electronegativity, like carbon and hydrogen has a very small electronegativity, and so you get nonpolar covalent bonds, equal sharing, or polar covalent bonds. And so that can range in magnitude. So you can actually calculate a dipole moment for that as well, right? So what we're doing is, if we're looking at electronegativity, the difference between two atoms, right? So in this case here, we have two chlorine atoms, and so we know they are equal in electronegativity. Just looking at the difference, there's a difference of 0, so there's a completely nonpolar. All right, and here H and Cl, hydrogen and chlorine, has a difference of 1.5, so that's a polar covalent bond. If it falls between 0.5 and 2.0, it's polar covalent, although it can have different degrees of polarity. And then KCl is a rather large difference. It's like 2.34, and that means it's ionic. So what you do is you look at the difference to see if a bond is polar. Okay, a molecule overall can actually have polar bonds, but it can be non-polar, because symmetry is also important. We'll get to that later on. Again, here we have no difference. This we did already, and this is ionic. And so that's just the bond, right? A covalent bond in which bonding electrons spend more time near one atom than another. I have actually a really nice picture for that, right? So here, if your difference in electronegativity is Tro, the author of your book, has the cutoff at 0.4, and so the nucleus is here, and Cl2 or H2 would both apply. And so the electron density here, what is around it is the electron density is distributed completely even here, and equal sharing, so therefore non-polar. And then as you increase that difference in electronegativity between two nuclei, you draw the electron density more and more towards the more powerful electronegative element, right? Let's say this is fluorine and this is hydrogen, for example. So you have a push. And so this blue region here is actually a partially positive charged region, right? Because now you still have that proton in the center, and it will create a partial positive charge and a partial negative charge. And so now two different HF molecules can stick to each other, and this is called an intermolecular force. So something that's polar covalent will have strong intermolecular forces, will therefore have lower boiling points and lower melting points because they stick to each other. And molecules that are completely nonpolar, they don't have strong intermolecular forces, so they tend to be gases, although the size also matters. And then if that electronegativity gets too high, or the difference in electronegativity is too larger than 2.0, that electron cloud is completely pulled away, and you get cations and anions, and that's what ionic bonding looks like then. Okay, but this chapter focuses mainly on covalent bonds and polar covalent bonds, right? So this is from your book. I don't know the page, but it's example 5.1. it has you classify bonds. And so you can go out and say, oh, okay, strontium is a metal, fluorine is a nonmetal. Pretty much guess, okay, that's going to be ionic, and you would be right? And then you have nitrogen and chlorine. Unfortunately, I don't have a periodic table, but I'll just put it up here, right? So you've got nitrogen. Let's do this. I don't want to pause and redo anything, but you've got nitrogen, oxygen, and fluorine, and if you have one, that'd be great. And then you have underneath, see, chlorine is here. So you've got sulfur and then phosphorus, right? So it's kind of hard to tell depending on the trends, right? Because you have an increase and a decrease, and so nitrogen and oxygen, it's hard to tell what the difference is. You can look up the difference, but if you had to guess, probably you don't know, right? And the same for nitrogen and oxygen. So you have to go and look up the values. Just looking at the difference isn't going to tell you. It will for strontium and fluorine. Let me just go to that electronegativity table here, right? So without looking at the here's strontium, okay, right? So strontium is a metal, and fluorine is the most electronegative. So good guess here, that being rather large and being ionic. But see, nitrogen is 3.0 and chlorine is 3.0, so that's actually completely nonpolar. And then nitrogen and oxygen is just barely polar. Nitrogen is 3.0 and oxygen, and I'm scribbling way too much over this, so it's 0.5 is the difference, so it's just barely ionic. Okay, not ionic, polar covalent. It's barely over this line, right? So it's weakly, but since you would call it polar, if I ask you this on an exam, you would call this a polar covalent bond. Anything past zero point 0.4, nonpolar, and then ionic. Okay, so you get the idea. And then so you can actually calculate something called the dipole moment. And that has to do with dipole moment could be mu. This is in your book, but I don't expect you to know this formula or work with it. Q is a charge and R is the distance. So if this is usually measured in coulombs, and depends on if you have a +2 and a -1 ion, or a +3 and a -2 ion, or +1 and minus. So it depends on the charge. You can calculate the charge and also the radius here. But for sure, the difference in electronegativity indicates what your magnetic moment is going to be, and D here is measured in dBi. So that's what dipole moment is called. And you can see here that if you have a nonpolar covalent compound, you have a dipole moment of 0, and then as your difference in electronegativity goes up, your dipole moment goes up. All right, so what is it exactly that happens when two atoms bind? Here you have the distance starting with 0 when they're overlapping, or let's start over here when they're pretty far away and they're not interacting. All right, so here you have two hydrogen atoms, each with one electron, so they have their spherical electron cloud. Remember, it's in a 1s orbital, and that's a sphere. And so there's one electron there. And so the potential energy is somewhere here right below 0. Okay? And as they get closer and closer together, they actually start to interact, right? At some point, these two electron clouds are going to overlap. And when you start to overlap them, they can start to share electrons. And that's when you get a drop in energy here, right? So everything is about wanting to be lowered in energy, right? Nothing wants to be in a high state of energy. So this is the preferred state. So when two hydrogen atoms approach each other and overlap, they form the most stable constellation at 74 picometers. Okay, so that's when you have, and so this would be drawn like that, where this represents two electrons, of course, an electron cloud, right? That's representing that, so that we are more clear about what that is. There are two hydrogen atoms connected by two electrons, right? And so this is kind of what it looks like. Okay, so what do these Lewis structures look like? How do we draw them? Some of them are straightforward and easy to come up with, but some of them are more complicated, and we need to follow some rules. But essentially, what you have is you have atoms here, two hydrogen atoms, and you count up all of the valence electrons. Those are the ones available for bonding. Right? Hydrogen is easy because you just each have uh, an electron. It's just what we just looked at, right? And so as they approach each other, they form a single bond, and this is how both hydrogen atoms fill up their valence shell, right? So 1s2, both of them get a full valence shell, and that's what it's all about, right? And so for hydrogen and bromine to interact, you consider, again, you can look at all of the Lewis dot structures. You can consider them. Bromine is in group 7, therefore it has 7 valence electrons. You put 7 dots around it, and then you realize rather quickly that, okay, so this is going to form a bond where bromine now has a full second period sharing that electron with hydrogen. The gaining, see if this was an X, it would just put it into here, and then hydrogen just needs 2. So they share electrons. And NH3 then gets a little bit more complicated. Nitrogen has 5 valence electrons, but it's not that complicated to see that it would make 3 bonds. And it requires, see, in order for nitrogen to get its 8 electrons, it's going to need 3 hydrogens, right? But you will be provided with a formula, and I am going to ask you to draw the structure, right? Okay, so let's take a look on how to do it. And so here I've just taken a shortcut. I've drawn a line, right? If a line represents 2 electrons and a bond, why can't I put a line on top of a nitrogen? And 9 out of 10 times, especially in this class, you are only going to see electrons that are paired up, right? So they're always going to be 2 together, either as a lone pair. This is called a lone pair because it's not bonding, or a bonded pair, which is what this is here. This one is bonded. And so these are 2 electrons that always stay together. There are instances where you have a single electron. Those are called radicals, and they are not stable. They react very fast and violently, radicals, right? So we are not going to encounter many, if any. And so I'm going to show you how to draw some of these Lewis structures. And once I'm done with it, I recommend that you do the Lewis structure lab and practice drawing them, okay? So here's a couple of examples, right, of Lewis structures, and then and so those are called, they're not called covalent bonds, they're simply called covalent bonds, right? If you have an electron from each orbital, like nitrogen did, okay, just looking at this and having a direct overlap, that's called a covalent bond, right? A donor covalent bond is when sometimes you can have a lone pair that forms a bond, okay? All right, so think about this. You here have, let's take a look at the periodic table and review what nitrogen's electronic configuration is without, well, we have 8 electrons here, right? So we have helium, 2s2, and then 2p3, but we have everything filled up, so it's actually 2p6, right? So we have 6 electrons. We have the here, right? So 1, 2, 3, 4, 5, 6, the 2 from the s, the 7, 8. So there are 8 electrons here, right? So we have all orbitals are full, okay? And you can have a molecule that where you have like this, BH3. Boron has 3 valence electrons, okay? It really needs 5 more, right, in order to get 8. But it can actually form, and it will do this initially, and boron is one of these exceptions here, right? It will make 3 bonds with hydrogen. and then it still has an empty p orbital. Okay, so there is another orbital, and uh, well, I'm just going to draw it like that. Okay, so there's a p orbital here, and it's empty, and this nitrogen, an element, or even water here, an element and a molecule, sorry, not an element, a molecule that has a lone pair available, can actually donate into an empty p orbital here, right? And that can happen with d orbitals sometimes, but we'll look at that. That's valence bond theory now. Now for now, just understand that that would be a coordinate covalent bond where both electrons come from one element, not one from each element. So you have this nitrogen that at this point is perfectly content because it has 8 electrons due to one lone pair and 3 bonds, and you got this boron, which is also kind of okay, but it has that empty p orbital, right? See, this one just has 6 electrons. This one has 8 electrons, so it can actually take this lone pair here and put it in there, so you can form a bond here. And once you draw that bond in like that, you can't tell that this is a donor bond. So if you want to indicate that, you draw a little arrow that these 2 electrons come. But it doesn't hurt the nitrogen, right? Whether the lone pair is there or a bond, it still has 8. You see? But what happens to boron is it gets 8 from forming that. So the incentive here is that boron wants that electron density and will form this coordinate bond. Okay? If you don't quite get that, that coordinate covalent bond at this point is not that important. Use the number of valence electrons and make a put together a structure that where everything has 8 electrons, and you're fine. Okay, so I'm gonna take a little break. If you have air, you should a little energy, you should keep going. I'm going to start the next recording. Well, you already have it in front of you. I haven't recorded it yet, but it's already there. So it's one of those Einstein things, I guess. Okay, so I'll stop rambling now. Thank you. Come again.